Okay, hello everyone. This is Fernando from Alicanto. We're here just to try and display the challenge number 2, linear regression for the MNIST dataset. Okay, first of all, let's explain our procedure a little bit. It's not that difficult. We just, first of all, try to get the data. And to get the data, we just use like the normal procedure. Okay. We extract, we download it. After we download it, we just extract it and just trying to transform this into CSV files, right? We're not going to explain the dataset because we all know already how this dataset works, so I think it's not a problem just to explain this again. So let's go to our procedure. We can see that first of all we try to review one sample of the dataset. We can see right here in this matrix how this handwritten number was drawn right here, was represented here in this matrix. Okay, after that we try to implement the linear regression. That was like the main point of this challenge. First of all, we just assume that X train and Y train, as you can see right here, are the training data and the labels. Okay, where X train is a NumPy array. The Y train as well is a NumPy array. First of all, we try to add a bias term that is a column of ones just to the future matrix X train. Also, we just compute the normal equation to find a beta. Okay. Another way of solving the singular matrix problem is using rich regression. Okay. To use rich regression, which just computes the parameter vector beta using rich regression, that is also the regularization. Also, we got two new parameters that are x and y, where x is the feature matrix with the bias term and the shape, right? And the y, that is also a NumPy array who has like the target vector and the shape. And of course, lambda, that is the regularization parameter. We, after pass for some computations for each one of the values that we are going to use later on the calculations just to get beta, right? And then after we have the beta, we have to take some to make the predictions using that learned beta, right? So that way we can just collect or return the predictions. Of course, we have continuous outputs, so we have to convert that again to integer labels, right, in the range 0 to 9. So after we convert that, we have to calculate the accuracy of the work, and we can see right here that all this function is just to calculate the accuracy. Okay, after we have our functions already defined, we just try to use it inside our data. We prepare our data right here. We can see after that we just compute beta using the training data and make the predictions on that training set. Okay. Of course, we are trying to calculate accuracy as well, just to make sure of the values that we are getting from this, and then after that make the predictions on the test set and to calculate the test accuracy finally. Okay. After run this, we can see that we have a training accuracy of 23.47%. That is with along with the test accuracy that is 23.01%. We can see that is maybe not the best way that we can just get this because the accuracy is still very low. Okay, it's less than 1/4 of the whole accuracy, right? So after that, we have to assess our predictions, right? So to assess the predictions, we are going to use a confusion matrix, and we can see right here in this confusion matrix right here that it's not that accurate, right? So we can see that the values are just distributed. We can see almost the diagonal right here, but it's still not being like correctly adapted to our data. So after that, we just create some data frames with true labels, predicted continuous values, and the predicted labels. Okay. Well, we try to make some visualization so we can see what is happening right here. So we can get in this plot right here, we can see that we have the true labels and the predicted continuous values, and we can see that our data behavior in a more like um, visual way, right? So right here we have like the box plot that is the predicted continuous value for each true label. So we know that we don't have like a good result, so we're trying to modify the beta just to find if we can achieve better results. After doing this, we can see that we have first 25 percent, 23%, 23, 23, and 23. So we see that using the raw data doesn't give good results. So we have to apply some. We tried to apply some convolutions to see if we can obtain a better performance. Okay, we define some kinds of convolutions, and we try to apply to the samples, right? In this example right here, we can see one sample that in which we applied some convolution, and we end up for something like this, right? Of course, we after that we explore how the different morphological operations affect these numbers, and we can see right here uh, in some samples how these convolutions or the um, morphological operations works, right? We can see that some of them works well for some numbers, and some of them just work for other numbers. So we don't have something specific, okay? So we just end up with something like this. We also try to use Fourier analysis, but after use the Fourier coefficients as the features to use for the linear regression, it didn't work. So yeah, after applying the different combination of these filters to the image and testing again and again and again, the results were not good. So the prediction just matched the average, and then we give up on this attempt and try to move forward because we just conclude that this is not the correct way to operate or to proceed, right? So we try to use the dimensionality reduction using the variance analysis. Okay, we only use the top 300, the top 10, and the top 50 features with the most variance. We hope that this selection of features give us more useful information overall. Okay. First of all, trying with 3 sets, we can see that we have an accuracy of 20.18%. With some other proofs, we get other testing, we get 19 and a 14 right here, 15 as well. So we conclude that we have not very good results from this, right? We just have the opinion that is curious to see that we can obtain an accuracy that is not that far away from the model with raw pixels as input, right? But half the amount of features. However, we have to look for a new approach. again. We have the second method that is try one-hot coding with regularization. Trying to guess all of the numbers with one continuous output might be not a good strategy, so we compute instead the probability of one image being a number and choose the highest one right here. So after implement this method, we can see that we have an accuracy of 85.34%, which is like most acceptable, I think, that the 20% that we just got last time, right? So we can see right here that we plot a confusion matrix for this method, and we can see right here a more uniformly distributed elements that we can see right here labeled the main diagonal, so we can see that is like a better approach, right? As we can, as I just said, the model seems to perform way better than anything that we tried before. Let's stick with this one and use it to complete the other task of the challenge. Well, let's go to the interactions terms right now. First of all, we extract the terms and select the right ones right here. We have all the code right here, right, and all the processed images, and trying to extract their features from that training data and also from the test data, right? And we can see that training the rich regression model, we get an accuracy of 94%. That is quite surprising and quite good as well. Okay, right here as well we can see the confusion matrix, and we have something very uniform, so I think we can trust on this method, right? Right here we have the model accuracy versus the lambda plot, and we can see right here that for some levels of lambda we can see more accuracy for the test, but it's not that regular. Okay, so we can see right here in this range right here, we can see something very stable, but under this it's not that stable. Trying the KNN model right here, we can see that we have we just implemented directly, and we can see that we have an accuracy of 96.88%, which is pretty good. And finally, the gradient descents. So we try to implement this using some built-in elements of the libraries. We can see right here using some iterations, like the more we go to the iterations, the loss just decrease and the accuracy just increase. Okay, so we can see right here in this plot how it behaves. That we can see that when we increase the iterations, the training accuracy in percentage will increase as well. And we can see right here that it's maybe approaches to this. I don't know if it is an asymptote, but it's quite likely to, right? We can see right here that we trying to express something. We try to express something with the gradient, right? To the gradient descent with the learning rate. O sea, we are going to take some learning rates, and we are going to see how this method behaves with these learning rates. So we choose some of them right here. We can see in this plot right here the learning rates and how the training accuracy behaves. We can see something very cool right here, that is like these lines are all over this one right here. Okay, but with the yellow line, that is the learning rate of 0.010, we can see some strange behaves right here that we can interpret it because the learning rate is like a little bit high, the adjustments that it makes is like very um, exaggerated. They're too strong, so it behaves like this. But we still don't know why this is like below these lines and not above them. So we really mm, don't reach why this happens, but it's just what we think until now. Okay, so after this, we can see right here that everything is done. So yeah, that's everything for us. Thank you very much.